Welcome back to the fourth video about capacitive liquid level measurement. In the previous video, I showed you the third general possibility of measuring the capacitance of such a capacitive sensor, and that is an RC oscillator around a Schmidt trigger inverter. Card here, link in the description. In this video, we will actually go digital and measure the capacity with a MCU. That is, in this case, an Arduino Nano Every. That is, we are going from analog to digital. Enjoy! I already got a working RC oscillator here that we built in the previous video that changes its frequency with the capacitance of our sensor, that is the fill level in our container. So all we have to do for now is measure the frequency of that oscillator with our little Arduino. Hardware-wise, all I did was connect the output of our oscillator with a digital pin of my Arduino, and that's digital pin 21. According to my oscilloscope, my oscillator is currently running at 7 kHz, about-ish. Now let's have a look at the code. So far, that's basically the same code I have here we already used when measuring the RPMs of a drill using a Hall switch. Card here, link in the description. Anyway, I have here a constant byte for my oscillator pin. I already told you that's pin 21. Please note, if you are using a classic Nano V3 with a 80 mega 328, you can only use pin 2 or 3 for interrupts. And we will be using that pin for an interrupt. I have here a constant unsigned in, that is my measurement period in 500 milliseconds. And I have here a volatile unsigned in cycles, that's the number of cycles we will count inside the interrupt service routine, so it must be a volatile global variable. And then in the setup, I initialize my serial interface. I want to see something on the serial monitor. I define that my oscillator pin is an input, and then I attach my oscillator pin interrupt service routine on the falling flank of my waveform, my square wave that's coming out of my oscillator and is fed into pin 21. It really doesn't matter if you count the falling or the rising edges. My oscillator pin interrupt service routine does nothing but increment that cycles variable, okay? And it might take, because we have an 8-bit CPU, that's a 2-byte unsigned integer, that might take half a dozen CPU cycles or dozen CPU cycles, but we are operating the oscillator in the kilohertz range, and the Nano Every is working at 20 megahertz, so that's okay. There's not much happening here in the loop. I have here a variable, cycles measured, which I use to buffer the contents of my cycles variable, which I initialize to 0. Then I wait for the measurement until the measurement period has passed, just a delay, very primitive. That was 500 milliseconds, remember that. And then I store the cycles variable, which was hopefully incremented by my interrupt service routine, into the cycles measured variable. And then I print out the cycled measures as a cycle. Then I convert my cycled measured, considering the measurement period, into hertz. And I also convert my measurement period and cycles measured into a period of milliseconds of my waveform. And that's it. And indeed, if we look at the output on the serial monitor, we are currently measuring 6.8 kilohertz, and the oscilloscope says 6.8 kilohertz. So we see there's a lot of jitter here, but in fact, because we average over 500 or count our cycles over 500 milliseconds and then average, the noise here, the frequency noise, is really, really low. It's maybe plus minus 2 hertz. We have here plus minus 1 cycle. Yeah, it's good. It's good. It's really a low noise signal, and we love that, don't we? I will remove now the oscilloscope probes because they are in the way of progress, and then we measure our frequency again with our Arduino, knowing that we are actually measuring the frequency. Please note that without the oscilloscope probes attached here, we are now oscillating at about, let's say 20 kilohertz, or if I'm very not going near there, sorry, let's say 20.5. Yeah, I'm rounding up here, 20.4 kilohertz. A little insert at that point. We will continue with the experiment in a minute or two. In the previous video, we talked a lot about how parasitic capacitances are messing up the behavior of our oscillator. And we just saw that just by removing the oscilloscope probes, our frequency jumped from 6.7 kilohertz to 20.4 kilohertz. And I didn't even mention the influence of the oscilloscope probes in the previous video. So here's some errata/addendum to the previous video. If I measure the capacity between my two probes, which are still connected to the oscilloscope, then my multimeter here is showing me a capacity of, let's say 33 picofarad. 33 picofarad. Given the multimeter without anything connected measures about 2 picofarad, but that still means that between the points where we connected our oscilloscope probes, we had a parasitic capacitance of about 30 picofarads. Also shorting out, at least, pulse-wise, when the polarity of the output changes, the output and the input. And and by the way, we are here up at 10 mega ohms. That was the last change I made in the previous video. And beforehand, we were talking about a few picofarads, and those oscilloscope probes here added here that parasitic capacitance of about 30 picofarads. And that's not all. If we measure the capacity of such a probe to ground, we get something like 46, or let's say 45 picofarads. Oh! That really isn't interesting here at the output, which is a relatively low impedance directly driven here by our Schmidt-Trigger inverter. But at that point, that means we have here another capacitor going to ground with, approximately 45 picofarads parallel to what we want to measure. You see how things are getting complicated. Let's measure also real quick the resistance we have here. That should be about 10 mega ohms. And yep. That's about right. So yeah, it should be 10 mega ohms because I put my probes here to 10 to 1. It's pretty much spot on 10 mega ohms. So the probe on that side also introduced here a parasitic resistance to ground of 10 mega ohm, and yeah, we're charging the whole system over 10 mega ohms. So that really also had a significant influence on how the whole thing behaves. And last but not least, let's see what's the resistance between two probes. That should be at least 20 meg. Okay, that's about 30 mega ohms. So we can almost forget about that. Nevertheless, having here, another resistor connecting our input with our charge point here of about 30 meg. So yeah, all in all, the oscilloscope messed up our oscillator quite good. And now let's continue with the experiment. Now, probably no longer visible because I'm now filling up here to the 100 milliliter mark. Yeah, that's it. And we're down already to, oh wow, let's say 10.6 kilohertz. And I go to 200 milliliters. Yeah, spot on. And we're down to 6.5 kilohertz. 6.5, yeah, 6.5. And 300 milliliters. That was a little bit much. Yeah, please note that that was a little bit too much. Let's say 4.1 kilohertz. We keep that in mind that I put too much in here. And 400 milliliters. Rounding up 3.1 kilohertz and 500 milliliters. 2.5 kilohertz and 600 milliliters. Oops. Yeah, I will correct that in a second. 600 milliliters with our sensor actually in the middle. 2 kilohertz. Yeah, let's say 2 kilohertz. 2.1? No, 2 kilohertz. I took the values we measured and put it into Excel to make a nice graphic. So here the reddish line, that's our frequency, and the scale is here. And we saw as we filled up from 0 milliliters to 600 milliliters, the frequency decreased, as we learned in the previous video, from 20.4 kilohertz to 2 kilohertz. And then I have here the light green line. That's the period of our oscillation. And that went up from, about 49 microseconds to about 500, or exactly 500 microseconds. And as you can see, you can fit here a line, the darker green line, almost exactly through it. And that's exactly what we want. A linear relationship between our level in our container and something we measured. Here are the raw values in my Excel sheet that I used to create that graph here. We were not spot on at the 300 milliliters, so I marked that red just for me to remember it, but obviously it didn't really matter. Anyway, Excel provides a function. This is German Excel, so I have the English names here. A function named line_est or linear estimate that can calculate you from such numbers the parameters for our line, which is mathematically usually given as y. Your y value is equal to m, that's a constant, x plus b, so a certain offset. I just called them here b and a. So b is our multiplicator, how steep the line is, and a is the offset. And in our case, with these numbers here for milliliters and period, here given in microseconds, I come to 1.299 and minus 27.401. Please note that here in this calculation I turned the axis around. So now the milliliters is the y that I want to calculate, and the period of our oscillation is the x value. I've added our conversion that we just developed in Excel from our oscillation period to volume to our code. So I have here first a constant float conversion factor, that's our 1.299. That is multiplied with the oscillation period in microseconds and should give us a volume in milliliters. And then another constant float here, conversion offset, which is minus 27.401 milliliters, so volume. In the loop, I now print out the frequency in kilohertz instead of hertz, and the period in microseconds instead of milliseconds, like we saw it in the Excel. And in addition, I print out the volume that we have filled in our container. So again, the period of our oscillation times our conversion factor plus our conversion offset. Now let's see. So here's a serial monitor, and the first thing we noticed here is we're no longer at 20.4 kilohertz. We are now at 21.8 kilohertz, and the thing is, it's really about the arrangement of my leads here that does influence the frequency quite a lot, actually. There is a reason why the Lord gave us shielded cables. We will have to live with that. So we are off to a bad start, but anyway, I will now add water again until we get displayed here 100 milliliter, and then we have a look-see where we are actually at. Well, it's not that bad. Our 0 point was off, but the 100 milliliters is not bad. Let's go. I'm looking again at the screen to 200 milliliters. Yeah, I'm making waves here, and that is actually, maybe almost. And we are 200 milliliters. So 300 milliliters. Okay, 302, and we're at 300 milliliters. 400, same game. And you can really see while I'm pouring, the measurements are a wee bit off. Yeah, too much again. 411, 410, and yeah, we are off. We are definitely a bit off on the 400 milliliter mark. Not dramatically, but we are off. So 500. Okay, our sensor starts to move. That's not good. 495, maybe a wee bit more. 498, good enough. Are we on the... yeah, we hit the 500 millimeter mark again. That's the problem with yeah, a linear approximation. Sorry for that bump. And 600 milliliters. 589, 59, a little bit more. Oh, that was too much. That was too much. 615, and yeah, we are a little over 600. And it's going down again a bit, 603, and we're here at 600, a little over 600. Yeah, all in all, not a high precision measurement, but it works. It works. And I'm sure if I would use here some coax cable, you can see how this is changing our fill level extremely. If you would use some shielded cable here or coax cable, and the sensor would be of a better quality and really fixed in our tank, things would look even better. But just for, you know, cobbled together thing, that's not too bad. That's it for today. Next time we will measure, that is, convert analog to digital, the capacitance of our capacitive sensor without the help of an external oscillator. And yeah, you see I in between made another improvement here. Changed at least to twisted pair, even if I don't have a coax cable, a suitable one. But yeah, we're getting better, step by step. So, till then, bye.